Welcome to lesson 5, and what we're going to do here is take a look at how energy is conserved. You guys are familiar with the law of conservation of energy, and so what we're going to do is draw a simple energy diagram that relates how the energy changes during the reaction where NaOH dissolves in water to produce Na plus OH minus. That would be the reaction that we have over here on the left of the screen. We talked about this reaction in detail in lesson 4. We're also now going to compare this reaction, which we know to be exothermic, to the reverse reaction, and this is where we would take sodium ion, combine it with hydroxide to make NaOH. So the goal is to draw this simple energy diagram. Now let me remind you of a few things. Firstly, the reaction on the left, NaOH dissolved in water to make sodium ion and hydroxide, is exothermic, and that means that we're producing energy as one of the products. So again, if you were holding a cup of water in your hand, cupping the glass, and you added NaOH to it, you would feel the water and the glass in your hands heat up. In fact, it would be kind of like a hand warmer. And this is a major characteristic of exothermic reactions. Let me get my label up here so there's no confusion. This is exothermic because the reaction produces energy. It produces energy like a product. All right, now, the opposite reaction, all right, so we're literally taking the exothermic reaction and we're running it in reverse. Notice how this reaction over here, written left to right, has the sodium cation combining with hydroxide to make NaOH. It's the exact reverse of this other reaction. And the reverse of an exothermic reaction is an endothermic reaction. Endothermic. And this means that energy is being absorbed in order to drive this reaction. So technically speaking, let me find a different color here. Technically speaking, we would be adding energy. See if I can squeeze this in here. To this side of the equation. All right, and I think what I'm going to do is just put a line down the middle of this thing. Well, okay. We have to get rid of some of this. All right, I'll just leave the line up here about halfway, just to separate the business. All right, so what I want to do next is we're going to draw an energy diagram. All right, and so let me lay the foundation for this so that we understand, that you guys understand what the axis means. So I'll start this over here. The vertical axis is where energy is going to be, and then I'm going to take this thing all the way across to the other side of my whiteboard. And what we have on the vertical axis is potential energy, and I'm just going to define it as capital E. And this value, this potential energy, is rising as we go up. So it starts at 0. Let's say it starts at 0 so that you understand. And then as the axis, the y-axis goes up, the potential energy is increasing. And we have the same scale on this side, and it's doing exactly the same thing. All right, and I'll put an arrow here to make sure you get it, that we're starting out at 0 potential energy and we're increasing, going up. All right, now let me put a label on the E so that we have no confusion. So this E is potential energy. All right, and we have the same thing over here. So this is PE. Potential energy. Remember the previous videos. Here we're talking about composition. Maybe I'll put that over here in the corner. This is all about composition. The bonds that are breaking versus the ones that are being formed. Now, I'm going to pick an arbitrary place. This is a qualitative diagram. I'm going to pick an arbitrary place to put my reactant, the NaOH. Okay, we'll put it here, and we'll define this point as being E1. So this is the potential energy of the reactants to start with. After the reaction is over, we've had, to be explicit about this, remember that NaOH is an ionic compound, right? So it has an ionic bond, and those bonds have to be broken. And then the Na plus and the OH minus, these guys are going to be interacting with the water. They're going to be bonding with the water. All right, so we have bonds being broken and we have bonds being formed. And the bonds being broken have a certain potential energy. And the bonds being formed also have a certain potential energy. Because energy is released in this reaction, the potential energy of the the potential energy of the products is lower than the potential energy of the reactants. So I'm going to draw another line down below to indicate that. So we'll put it here. So get this as straight as I can across here. And this is where the products of the reaction are going to go. They're at a lower energy, and if we were to draw a line over to the vertical axis, like I'm doing here, we would define this as being E2. Now, if we take I'm just going to extend a dotted line out here so you can see closer what I'm doing. If I want to determine actually how much of this energy is released, then all I have to do is take the difference of these two lines. So the delta E here, which is going to be negative, is going to be equal to E2, which you can see from the graph is smaller than E1 minus E1, and the value is going to be negative. And what the negative means is that the energy is released. So energy released is what this means. It doesn't mean like we have less of it or something, or that it's a smaller value or some deal like that. The negative sign tells us what's happened to the energy, and in this case it was released. All right, now let's take a look at what happens with the reverse reaction. So in the reverse reaction, the reactants are the same as what the products were in the first example here. So I'm going to put my platform, to the best of my ability here, in exactly the same location. All right, and let me get these guys scrolled in here. So we're going to have the Na plus plus the OH minus. So in the reverse reaction, the reactants are the products of the original reaction we were talking about over here on the left, and so energetically they start in exactly the same location. So if I bring this over, doing my best to do a straight line here, then in the new reaction this is E1. In the reverse reaction, this is where we're starting. This is our starting point. Let me just clarify that. Whoops, I think I need a darker color. So this is going to be, this is my starting point. Start point. And we're going to now convert this to NaOH, which is going to have the same location as the NaOH on the other side. So I'll try to match this up. So it's going to be approximately here, and this is the NaOH. Remember, what we're trying to show here in this diagram is how the law of conservation works. So in the case of the reversed reaction, we're starting at the same point as the products in the forward reaction, and then we're going to end up in the same place as where we started in the forward reaction. Now, to find our delta E here, I'm just going to draw my dotted line over, right? And then I'm going to put a bracket here, and then I'm going to bring an arrow up. So the delta E here, to be really clear about this, is going to be equal to, well, and I forgot, see right here, this is E2. So in this case, and when you do this math, it's always E2 minus E1, all right? It's final minus initial. And so here you can see E2 minus E1. Now check this out, because you see E2 here now is a bigger value than it was in the forward reaction. So the outcome of this is that we get a positive value. So the forward reaction is exo, and the reverse reaction is endo. So we've actually had the reactant here is at a higher potential energy than the reactants, right? This product in this reaction, in the reverse reaction. So this is the product, and it is at a higher potential energy than where the reactant started. In the forward reaction, it's exactly the opposite scenario. So we start with the reactants at a higher potential energy, and we end with the products at a lower potential energy. So, but what's crucial here for you to understand is that the negative delta E that we had for the exo reaction is equal to the positive delta E that we had for the endo. So the magnitude of the energy change is exactly the same. The signs just show you which direction it's going. So in this case here, we had to increase the energy of the product. And that's the hallmark of an endothermic reaction. In this scenario over here on the left, we had to decrease the potential energy of the products, which is the hallmark of an exothermic reaction. So let me finish the video by putting that in words. All right, so for the exo reaction, the potential energy of products is less than the PE, potential energy, of the reactants. All right, and we have the opposite scenario. So for the endo, all right, the PE of the product is greater than the potential energy of the reactants. Okay, and with that, I'd like to close the video. Remember, as you go through this stuff, it seems complicated. Pause the video, think about it. If it's still a problem, then you need to go back and redo the video, and redo it as many times as it takes in order for you to understand the material. All right? See you in lesson 6.